One question is that the most suitable reagent for the following transformation. That is, here one unprofit unsaturated ketone is there. Here is a alkene. So we have to reduce only this double bond, and remaining will be same. So what reagent we will use? So lithium in liquid ammonia, that is Bart's reduction, PTO2H2, that is Adams catalyst, lithium aluminum hydride, and B2H6. So what will be the answer? As we know that if we use PTO2H2, that is Adams catalyst, then it will reduce the carbon-carbon double bond, this bond also. So this reagent will not be used. Lithium aluminum hydride will reduce this alpha beta unsaturated ketone fully to alcohol. So this will not be used. In B2H6, it will reduce this double bond also. So the option is lithium aluminum hydride. This batch reduction condition reduce only this double bond and it will remain intact. So the answer will be lithium aluminum hydride. We'll draw the mechanism. We'll take this person only. First, lithium will give one electron. Electron will be given here. So it will be minus. Here 2 electron movement will occur, and here will be 1 electron. Now another electron will be given. So it will be O minus. Here will be a negative charge. Now from NH3, it will take one proton and will be converted to the enolate anion. This is enolate anion. Now in this condition, Li liquid NH3, this will not take proton because NH3 is stronger, NH2 minus, which is a strong base, than O minus. So it will take the proton again. So this is stable in liquid ammonia. So after this, if we acidify this reaction condition, then it will be converted to OH, and then it will analyze to the corresponding ketone. And that's why in liquid ammonia condition we will get the product like this, only reduce this double bond only, but the keto group will remain intact. Next question, the major product formed in the following reaction. Here 2-hydroxypyridine is treated with CH3INOH and CH2N2. What is M and N? So first, if it is treated with CH3I, then this lone pair, here nitrogen has one lone pair, oxygen also has two lone pair, but this lone pair will attack into this CH3, and so what will happen? It will be, this will produce, and then OH minus will take this proton, this will be the product. Now if it is treated with CH2N2, then what will happen? CH2 into it will take this acidic proton and now this will converted to a good leaving group, so it nucleophilic substitution will occur and two methoxypyridine will form. The next question is the major product formed in the following reaction. This is methyl acetoacetate, this is methyl acrylate in presence of NOMe, MEOH. So in presence of a strong base, what will happen? Here two acidic hydrogens are there. Why this is acidic? Because two C double bond O carbonyl group is there and they are pulling electrons, so these hydrogens are acidic. So what will happen? In presence of a strong base, one of these proton will be abstracted by base, so the corresponding enolate will be formed. Now this enolate, which has the negative, it will have this is an ambidentate nucleophile actually. Here the negative charge may be in oxygen and also it may be in carbon. So this is the soft center, this is the soft center, this is the hard center. Now in presence of a alpha beta unsaturated ketone, here one pore addition will take place, that is this soft center will attack into this position and one pore addition will take place. So what will happen? If it will attack here, then this will be formed. So this will be formed, and when it will come back, it will take one of this proton from this alcohol. So the product will be this. This reaction is known as Michael addition. This is a one pore addition. This reaction is known as Michael addition. So this will be the product. Next question is the major product formed in the following reaction. This compound 2,2-dimethoxypropane in paratoluene sulfonic acid as catalyst. So what is 2,2-dimethoxypropane? This is 2,2-dimethoxypropane. So if in presence of PTSOH, what will happen? In presence, this is actually the kettle of acetone. Kettle of acetone. So in presence of acid, it will converted to, I'll draw the mechanism. In presence of acid, it will be protonated. So OH Me plus OMe minus MEOH. All this step will be reversible. double bond OMe plus, now this compound here, which group will act as a nucleophile, and we can represent this as a diol like this. These two are R group. So now this diol attack here. So plus should be OMe. Now this proton will be given by this O, and it will be taken by this, so minus H plus H plus. So it will be converted to this. Now this which will attack here, it will eliminate. So what will happen, and I am showing this in single step actually. So this will be the product. If we expand this, then if we put this R group, then the product will be COOMe, COOMe. So this will be the product. Next question. In the two-step reaction sequence given below, the starting bis-sulfone acts as. So this is bis-sulfone. Bis-sulfone. It acts as you know, as we know that this is the diene. This is the dienophile, and this is a Diels-Alder reaction. So bis-sulfone acts as a dienophile here, and if we see here that if the Diels-Alder reaction happens between these two compounds, then what will happen? The product will be this. So we are getting the same product here also. This compound is reduced to sodium amalgam, and it will be converted to this. So if we are using acetylene instead of this, then we are getting the same product. So this is the synthetic equivalent of acetylene actually. So this bis-sulfone acts as a dienophile here, and as well as synthetic equivalent of acetylene. And why acetylene is not used? Because here the rate will be very slow. So generally this is used to produce this compound. Here two electron withdrawing groups are there, so the rate of Diels-Alder reaction will be much higher. Next question. The major product formed in the following photochemical reaction is this compound treated with H nu. So what will be the product? As we know that this is the Barton reaction. Barton reaction. So what will happen here? First, how many carbons are there? 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. So first it will break when it will be photochemically irradiated. So two radical will form. Plus NO. Now it will take one hydrogen from alpha, beta, gamma, delta carbon. So it will take this hydrogen and one radical will form here. So it will be OH and one radical will be there plus NO. Now these two radical will combine to form the product NO. It will be OH. So this will be the product. Next question, the major product formed in the following reaction. So this is a diene. This is a dienophile. So Diels-Alder reaction will occur. Here this dienophile will come from below the plane of this diene. So if this comes from below the plane, then these two deuterium will go above and these two hydrogen will go below the plane. So the product will be here will be a deuterium above the plane and one below the plane. Here will be deuterium, one above the plane and one below the plane, and this hydrogen will go below the plane and this deuterium will go above the plane. So this will be the product. As this is a stereospecific reaction, so this will be the only stereochemistry. Here the deuterium will be on the same side. In the options, in the four options, the deuterium one is above the plane, one is below the plane, but this option will not be correct. This will be the correct answer. Next question, for the following alkenes 1, 2, 3, the rate of hydrogenation using Wilkinson catalyst at 25 degrees centigrade. So using Wilkinson catalyst, we have to the rate of hydrogenation, we have to determine the rate of hydrogenation using Wilkinson catalyst. So in Wilkinson catalyst, which is RHCl PPH3 whole 3, this is the Wilkinson catalyst. So Wilkinson catalyst reduce the alkene into alkane, and the rate will be higher for less substituted alkene, that is disubstituted. The rate of disubstituted, the rate of reduction of disubstituted alkene will be higher than trisubstituted alkene, which will be higher than tetrasubstituted alkene. Now as we can see here that this is a disubstituted alkene, this is also a disubstituted alkene, this is cis and this is trans, and this is a trisubstituted alkene. So the rate for these two will be higher than 3, and between cis and trans the rate of reduction for cis alkene will be higher than trans alkene. So combining these two, we can tell that the rate of hydrogenation will be this will be for a higher rate, and then 2 then 3. So 1 greater than 2 greater than 3. This will be the answer. Next question, the major product formed in the following reaction. This is treated with Ag2CO3 on chelate in benzene solvent refluxing condition. Chelate is SiO2, that is silica. So Ag2CO3, this reagent is known as Petterson's reagent. It is Petterson's reagent. This is an oxidizing agent and it generally oxidizes the allylic alcohol. So this is the allylic alcohol, so it will be oxidized to aldehyde, and then what will happen, this OH, this is a primary alcohol, it will attack to this aldehyde. So first it will be oxidized, it will get oxidized to aldehyde, and then this primary alcohol will attack this aldehyde to form a 1 2 3 4 5 member ring. It will be OH. Now this is called lactol. Now it will get further oxidized to a lactone. This is a lactone. So this will be the product. Next question. The major product formed in the following photochemical reaction. This reaction is a known reaction that is called dipymethane rearrangement. Methane rearrangement. In this reaction, what happened? First, these two pi bond will be homolytically cleaved, and here a 3-member ring will be formed, cyclopropyl ring. pH. Now between this in this biradical, this radical is much more stable than this radical, because two phenyl group are here, so this radical can come in conjunction with this phenyl group. But this radical, it has only stabilization by hyperconjugation with this 3-methyl. So now what will happen? This bond will cleave. So from this biradical, another biradical will be formed. This biradical will be formed. Now these two radical will undergo coupling to produce another 3-member cyclopropyl ring. So this will be the product. This reaction is known as dipymethane rearrangement. Among the following decahydroquinoline toluene sulfonate, the one that yield 9-methylamino E-non-5-enal as a major product. So first we have to see the 9-methylamino E-non-5-enal. So 9 carbon will be there, 3 4 5 6 7 8 9 methylamino. So one methylamino group will be there with this carbon, NHCH3, non 5-enal, 5 1 2 3 4 5. There will be a double bond here which will have E configuration. E means trans, so 2 hydrogen will be here in trans position, and one aldehyde group will be, this is an aldehyde group. So this is this 9-methylamino E-non-5-enal. So this will have configuration E. So now we have to see here that this is a decahydroquinoline derivative which has trans configuration. So this is if we draw this in chair, then here is a nitrogen CH3, OTS group is here OTS, and if we draw the another trans C, here nitrogen C is 3, OTS group is here on the above OTS. Now as we can see here, what will happen, this nitrogen lone pair will attack here, and as these two bonds are parallel, so this bond will cleave, this lone pair will attack into this bond will shifted here, and this leaving group will leave, because these two bonds are parallel, anti-periplanar to each other. These two bonds are anti-periplanar to each other. So what will be the product from this? Here the nitrogen C is 3, here will be a double bond, as well as here is a double bond. Now as you can see here that this two hydrogen is in trans, so this double bond will have configuration E. This double bond will have configuration E. Now if this group is hydrolyzed, this bond will cleave and it will be converted to one NHCH3, and this will be converted to CHO. Now OH2 will attack here, so this will be OH, will be CH3. Now it will be protonated, so it will be eliminated. So the product will be NHCH3, and after deprotonate this will convert it to a CHO. So this configuration will be E, and this is actually the 9-methoxyamino E non 5-enal. So from this compound this product will be formed, from this compound. So the answer will be option C. From this compound the elimination will not take place, because here the two bonds are not anti-periplanar, and these two, if we draw this configuration, this has this configuration, so here NCH3, the OTS are above the plane OTS. Now here also these two bonds are anti-periplanar, so from this compound elimination will take place, but the configuration of this double bond which will formed here will have Z configuration. So from this compound we will get Z, and from this compound we will get E. So our answer will be option C.